Okay, lovely to see everybody. I wanted to attend this meeting for quite a few years, and I've been invited to, but it's never worked out. So at least we can do this online version. So good afternoon to everybody who's attending. It's 6 o'clock in the evening for UK. So I'm not a propellantless propulsion person, and that's not really my background, but I understand this is a propellantless propulsion workshop. So it's a bit of a challenge for me to kind of talk on this topic because I mostly deal with kind of fusion and so forth. But let's have an attempt to talk about a few things. And I wrote these slides literally this morning, so I hope you're not too disappointed. So I thought I'd first of all describe a narrative of some views I have about propulsion, advanced space propulsion, and then sort of use that as a way to move forward. So it seems to me that most research that's done in space propulsion is of one of the following natures. It's a theoretical background research, just doing calculations to see what energy comes out of something, for example. Experimental investigations into fundamental physics, getting in a laboratory and actually trying to test things. And then integration of that technology into some vehicle architecture. Mission-driven studies for performance analysis, which is obviously very important if you want to talk about using that technology in space. Comparison to competing alternatives, and even in-flight demonstrations. That's when you go up the TRL ladder. And all of the above are quite important from an investment perspective in terms of how much money do you put into any area, right? This is a problem for organizations like the Limited Space Institute or the Breakthrough Initiatives who have substantial funding. Where do they decide to put that money? And how much should they put into, say, propellantless propulsion or other breakthrough modes of research? So although I'm mostly a propulsion person, my view actually that the tall poles in the tent is really payload and mission requirement. You know, you can't really compare, say, a grand scale Starshot probe to something like a world ship, right? There's a completely different architecture, systems, and so the payload and the mission requirement, what you actually want to achieve, is incredibly important. And the actual design of a mission depends on several factors, from the physics, you know, whether it actually obeys the laws of physics, or unless you're exploring alternative ideas for physics, whether you can practically build it, that's the engineering, whether you can fund it, whether it's with a government or private partners, what the politics are, you know, particularly if you're in a government shared program, in terms of moving that technology forward. Project Apollo was an exemplary example. Ethics is, you know, there's certain things we can't do today because of ethics, such as objections over the use of certain nuclear technologies. And then urgency, right? I'm sure that if there was a whacking big asteroid that was on its way to Earth and it was going to be here within 10 years and we needed to deploy some technology and get out there fast, that a lot of objections over certain technologies would be removed overnight because of the urgency. So this all governs what sort of research is favorable. There's various reasons for doing advanced space propulsion research, and I think this is very important in terms of thinking about new modes of operation, such as propellantless propulsion. There's obviously technological spin-offs to human civilization, hopefully in the future. These are good and bad, you know, military advantages against aggressor nations. If you have a technology that they don't have, that's obviously an advantage. Continuation of space exploration outwards, as we've been doing. Establishing independent human colonies, human colonization strategies to other worlds or even other stars, which is primarily my interest. You know, I have this running joke that I tend not to be interested in technology unless it hits at least 10,000 kilometers per second, because that's really what you need for sort of interstellar. Investigating new scientific discoveries far out, space mining industry, resource acquisition, and of course experimental platforms at relativistic speeds, lots of things we can learn about physics. Mitigation of incoming impact events. I mentioned the asteroid and cometary impact threats. And then the last one I've listed here, which is hopefully the least likely, but we should always be prepared for it, which is the possibility of extraterrestrial invasion. So, you know, that technology, that space propulsion technology, gives you an enormous armament of capability, which has so many broad applications. I think most of my work is theoretical. I'll be honest with that. I don't really dabble in experiments. I have in a previous job been involved with experiments, but I don't really do experiments myself, other than during my undergraduate studies with wind tunnels and things. But what I've observed, which is really gets me nervous a little bit, is when I see breakthrough propulsion experiments being done. I worry about the credibility of some of those experiments and the perception that gives off in terms of the optics to other scientists, right? So, I mean, there was an excellent book produced by the Tau Zero Foundation a few years ago, Frontiers of Space Propulsion, which explored a lot of the breakthrough propulsion fields. But things such as clearly stating assumptions and caveats and not overselling ideas and not conducting apples to oranges comparisons, as a part of an advocacy. So I often hear people advocating for specific propulsion technologies over others just because it's their expertise, when actually the numbers should drive that direction. And then publishing in peer-reviewed journals is really important for credibility. It can be hard. Some journals, I used to be the chief editor of JBiz, and quite frankly, I got fed up with reading hundreds and thousands of papers. I don't do much peer review these days because of it. I'm kind of dried out with peer review. But it's very important to try and get papers in journals, whether it's Actor or Icarus or Spacecraft and Rockets, whatever. It helps with the credibility of our field. And then in terms of specifically for experiments, I often hear people talking about experiments, and I don't see a lot of discussion sometimes on errors, systematic and random errors, standard deviations, which is vital for experimental confidence. And then, of course, we should be aiming to reproduce results. So this is really important in terms of the perception of the advanced space propulsion community to the rest of the scientific endeavor. And therefore, when it comes to the big bucks investors, why they should invest in our technology, it's important that we show that we have that academic rigor. And then finally, I think it's very important we take great care in our interpolation, extrapolation of our numbers. So it's very easy to sit there and do a calculation of some particles interacting and work out the energy that's coming out and assume that's an exhaust velocity and work out the thrust. And, before you know it, you've got a spacecraft, right, engine and a proposal. And then maybe you scale that number up to, if we invested X amount per year over the next 10 years or 100 years, this is where it could be, and we could apply it to that particular mission. I've seen people, have hard times at conferences when they try to oversell an idea. So I think it's important that we are moderate in our extrapolation specifically to make sure that we are, again, not overselling the technology. So rigor is really important. So I just thought I'd say that at the outset. So a few years ago, quite a few years ago, I was involved with the NASA DARPA 100-year Starship competition. I was actually on the winning team. And a part of that, I did a quick roadmap study. So it's a kind of, this was called the 4 days study. And the goal was to try and work out, a roadmap to get into a 2111 launch date, which is what NASA and DARPA set out at the time. So it starts with a kind of 200 AU mission past the Voyagers, 1000 AUs into the Oort cloud and out to the first Interstellar mission. And this is both crewed and uncrewed architectures. And the idea is that every sort of 20, 25 years, the generation of designers changes. So you're preparing for the next mission. There's a kind of stewardship. And it looks something like this. And this was eventually published only this year. I finally got around to writing it up and trying to get it published. But what it shows is the blue lines is the direct pathways for unmanned, or uncrewed, I should say. And the pink is for crewed. So you go for your research and development, construction, production, mission, launch, utilization phases, and you're trying to get to your launch date for those different architectures with your different generations. But the specific bit I want to bring to your attention is at the bottom, which is the gray scale. You notice it's on a time lag. Well, basically, you've got their existing, emerging, and vision technologies. So these were actually mapped to NASA TRL mission statements. At the time, produced by George Smith at NASA Glenn, and which he presented, I think it was at the IAC in Prague. And you see you've got the TRL 6 to 9, and that the idea is they'd be achieved sort of 2011 to 2021, and then 3 to 6 from 2021 to 2061, and 1 to 3, 2061 to 2111, because that was the constraint of the project, right, 2111. Well, in terms of propellantless propulsion, and anyone can shout out if they disagree with me. But most of the technologies we're exploring, from field propulsion to the beamer-driven systems or whatever, it tends to be at the low TRL. So it's down at the 1 to 3, and most of it, like warp drives, is arguably down at 1. It's conjecture. And so this is the kind of roadmap you have to build on a practical level to actually think about how we can have a program like Apollo going to the moon, but now we're going to go to the stars. What is that program? And so when you think about breakthrough propulsion technology, how does it fit into that program? It's down the road. Okay, so, and that's not a bad thing, you know, because it may be that that technology doesn't reach fruition for centuries. We just don't know. Or it could be that you know, someone discovers something about 0-point energy in a laboratory tomorrow, which changes everything overnight. But my point is that from an investment perspective, when you're looking at technologies to investing to move space exploration forward, obviously the low TRLs are much higher risk. And this is a problem in terms of finding funding. And it's an issue for those organizations that wish to fund such programs. So what this chart shows, this is something I did quite a few years ago, probably about a decade ago, actually. When I came into the field of interstellar propulsion and interstellar studies, I sat down and tried to map all of the interstellar propulsion methodologies that there were. No doubt there's lots missing. I know that my friend Greg Matloff's already pointed one out to me that's missing. You'll probably spot quite a few. But essentially what I did is, you know, in the universe, there's kind of space, time, mass, and energy. So what you've got on the left side is essentially, I call it the energy-driven designs. So this is the attempts to push vessels using the Tsiolkovsky rocket equation. So essentially you're going for higher exhaust velocity and trying to improve your mass ratio. So you go from the chemical all the way through to the fusion systems and the photons, pure antimatter. On the top there, what you're doing is you're not carrying your fuel on your vessel. What you're actually doing is beaming the fuel to your spacecraft, right? So this could be mass drivers, particle beamers, laser drivers, so or even the solar cells. You know, solar energy is leaving the sun. It's not actually on the spacecraft. It's arriving at the spacecraft, and it bounces off the spacecraft. So I call those the mass-driven designs because you're driving a mass through some remote, distant energy source. And then on the right-hand side, you've got what I call, I can't see it because I can see all your faces instead, but I call these the space-driven designs. And essentially this means you're not carrying fuel and you're not beaming the fuel to the spacecraft. What you're doing is you're catching the fuel en route, right? So this could be interstellar ramjets, where you're picking up interstellar hydrogen, the interstellar medium, or it could be field drives, such as bias drives, pitch drives, disjunction drives, where you're somehow engineering space or the quantum vacuum to pick up energy. And then on the bottom there, it gets really exotic with what I call time-driven designs, because now you're well into the field of general relativity with black hole manipulation, Krasnikov tubes, warp drives, and even time travel. And I put that there just for Doctor Who fans. And everything in between. But what I'm particularly interested in is the idea of hybridization of all these different methodologies, whether you could combine them or into, you know, to try and find some optimality route forward. So I'm going to come back to this map several times. So most of my research has been on the left side, and because I'm mostly fusion and nuclear, and also on the upper side with laser beamers. And I've dabbled a little bit in ramjets and warp drives and so forth. I'll talk a bit about that and wormholes. But a lot of the propellantless propulsion is kind of on the sort of east side and the south side of that map. So let's just start a little bit. So these are propellant-based systems, but I think it's important to have proper context. Orion, of course, you know, maybe with the hydrogen version, you can get to 10% the speed of light and get you to the nearest stars in just over a century. Orion technology is very unpopular because it's nuclear bombs. I happen to have a background in this area in my previous life, shall we say. But there are some problems with Orion, such as limitless specific impulse, and this is mainly due to the angle of the blast that's subtended, because it's an external nuclear pulse system, and also the length of the shock absorbers, which take time to sort of transfer that momentum and rebound. But you know, Dyson, who was involved with it with Ted Taylor, was known years later for being against Project Orion, for having changed his mind. But I had discussions with Dyson over the last 10 years about Project Orion, where he agreed with me that actually, although it's probably not right to launch one from the surface of the Earth, launching one in deep space where there's lots of charged fields and high radiation out there anyway is probably not such an issue. So certainly this is a technology we have today, could utilize today when that asteroid coming. But obviously, if you're someone like Bob Ford, you want to not move towards propellant-based propulsion, which is what his game was. Project Daedalus, I'm sure you've all heard of this. This is the BIS study from the 1970s. This has really taken Orion to a different level, shrinking it all, using much smaller capsules, deuterium helium-free, 50,000 tons propellant, getting up to 12% of the speed of light. And it's not really an internal nuclear pulse or an external nuclear pulse. It's a hybrid because the engine nozzle is open to the vacuum of space, but the capsules are imploded internal to the chamber. 250 times a second, which is a terrific amount. And so in 2009, I was involved in Project Icarus, launching Project Icarus with Richard Abusi. And that was quite a successful project, still going, would you believe, still trying to finish it. And we produced lots of different designs, but this is just one of the kind of ideas that we came with up the time. The idea was to kind of shrink Project Daedalus and come up with something a bit more credible. This is a multimodal system. This is one of the original diagrams from when we did the study, and it involved multiple modes of propulsion. So it was accelerated by a deuterium stage, then a proton boron, and then a deuterium helium-free stage, decelerated by deuterium helium-free, also using a mag cell, using something called a Medusa cell. So the idea was to minimize the engineering stress on all the individual modes by having lots of different ones. And we, as a team, we kind of decided that was too complicated and we need to simplify. So we moved forward to something like resolution, which is essentially like a Daedalus second stage engine only. Daedalus was 2-stage, but it turns around, reverses the thrust. This gets to the stars in 100 years, which was the Project Icarus requirement. It's fusion, deuterium helium-free. This looked quite good, but the main problem was the boost phase was like 15 years long, which we thought was too long. It burns at 150 hertz pulse frequency, which is shorter. But you know, the things that's going to go wrong in that time frame, the fatigue on the structure is really an issue. So we decided to parallelize the thrust profile. So the people working on this was myself, Richard Osborne, Rob Swinney, a bit of help from Robert Freeland, Michel Lemontagne. And this was basically taking a Saturn V Quintec engine idea and parallelized the thrust, and we got it down to about 3 years boost time. The problem with this kind of design is you're producing a lot of high energy neutrons and also X-ray radiation, which bombards the rest of that structure and heats it up. So we decided that we needed to put some radiators in there. So we moved to a 4-engine bell system. This is the current one. It's called Pegasus. So it's still carrying propellant. You can see there's big propellant tanks. For those of you that are into propellant propulsion, this is not something you want to see. But it's the latest kind of concept. Just to give you an idea, this is one of the few tables I show for these propellant-based systems. So this particular design, which has been calculated, is 22,000 tons deuterium helium-free for acceleration, 4,000 tons for deceleration. It has a jet power of 7.3 terawatts for the acceleration, 1.8 for the deceleration, specific power 1.4 megawatts per kilogram. So it's really a big system, gets on 100 years, and it gets up to a speed of, trying to find the cruise speed, 4% speed of light, just over in this particular architecture, to get to near stars in about 100 years. So I won't label much more on that. So this is the sort of problems we deal with. You know, whenever I've given talks at NASA labs, and I've been to every NASA lab, I always make sure I quote the big numbers, like the big specific powers and jet powers. It's my way of saying to them, look, I'm not in here claiming we can build a warp drive tomorrow. I know that propulsion is really hard, and you know, the amount of energy you generate is just crazy. So this is just that map again. So I then also started looking at laser-driven systems. I'm still looking at the fusion, but the laser-driven systems. I'm a huge fan of Bob Ford. You know, I'm sure you're all aware of his work from the 1980s, and when he designed the Star Wisp architecture. He was brilliant and designed flyby, rendezvous, and return stages architectures. And I've calculated all his numbers again in a code and wrote them up, and they all look really sensible. Of course, he's got this massive collimating lens, which is like 500,000 tons. That's to recollimate the beam due to the Rayleigh effect. So So I worked on a project a few years ago. I can just about see the numbers because I can't see you guys. But basically, we designed a project that moves at 10% the speed of light. It's gram scale, so it's like 20 to 30 grams in mass. And it moves at 10% speed of light, gets to the nearest stars in about 40 years. And it uses a segmented lens array. So this was a concept that in 1999 Jeff Landis came up with. It's the idea of using multiple lenses to recollimate the beam and to push it to, I think it was 11% speed of light. I can't see the numbers at the moment. But it's a cool concept. We presented that to Breakthrough Starshot in early 2016, prior to their announcement, and they of course had already been working with Philip Lubin and others prior to the announcement of Project Starshot. And I'm still working with Breakthrough, and I'm on the advisory committee for that. This is Breakthrough is moving forward rapidly with their excellent program, looking at launching gram scale systems using these multiple phased lens array lasers, accelerating something to thousands of Gs, 60 kilometers per second, 20% speed of light, and within a matter of minutes. And it's at the early days, but there's lots of really cool R&D that's going on. Lots of university teams have been funded, lots of contracts have been issued, and there's lots of papers being published by the team. So I'm really excited for Breakthrough in terms of that propulsion technology. And of course, it beams the propellant to the target, although it has a drawback that the payload is very small, although you can send many of them once the architecture is in place. Breakthrough Starshot, there's lots of technical challenges with Starshot. I've actually been specifically working on the particle bombardment problem because I think the dust problem is quite interesting. I won't labor over these different issues, but it's just to point out the nodal propulsion. One of the things I'm interested in, I mentioned on the landscape map, is hybridization of different technologies. So I presented at the Starship Congress in 2013 to Icarus Interstellar, which I was a co-founder of. And this was just a concept, I wouldn't even call it a vehicle because I didn't go much beyond this, but the idea was the Tchaikovsky rocket equation is really, you're deriving thrust through that exchange of exhaust velocity and that momentum push. But actually there's external forces that potentially could act on the vehicle. And so I saw those external forces as propulsion opportunities. So what you've got here is a vehicle that's being propelled by a reaction engine, like an ion engine or a fusion drive, but it's also being pushed by a solar cell. So it's got energy from the sun, which pushes it. And that's the first equation in the velocity term. And then the second one is a laser driven system. So once it gets so far out that the laser intensity, the solar energy drops off, which is sort of past Jupiter, you switch on the laser and you can push it even further. So it's like 3 modes of propulsion to try and push one vehicle. And there's very few studies I've seen where people have tried to combine different propulsion concepts. The Medusa cell is one of the ones I think has done that because it's a combination of solar cells and Project Orion technology. So interstellar ramjets are really interesting. 1960 was the first paper by Broussard. And I mentioned the interstellar medium, all that dust, but also there's lots of hydrogen. You're all familiar with this kind of technology, I'm sure. This is one of the beautiful graphics, by the way, from Cosmos, Carl Sagan's Cosmos by Rick Sternbach, and I own all the paintings and the drawings from the Cosmos documentary. I frequently take them to conferences to make sure people can see them. But the beautiful thing about the ramjet, of course, it doesn't carry its own fuel. So it is a form of propellant propulsion, except for the initial acceleration phase, right? Because you need to get it up to high velocity at the beginning with that fusion reactor before you can start picking up enough high energy particles, hydrogen in the interstellar medium to then pass that through your fusion engine. The problem is, it turns out that the interstellar medium abundance is an order of magnitude less than we thought in the sort of 60s and 70s. For Project Daedalus, that turned out good because it means they didn't need a 50 tons particle shield, which was 9 millimeters thick beryllium. I run those numbers and they don't need such a big thick shield after all. But the ramjet, the interstellar hydrogen has a very small cross section, and what tends to happen is the particles tend to pile up at the collimator, and so it's actually difficult to slow them down, moderate them, pass them through a fusion reactor. So there's practical engineering problems. There are other solutions such as the catalytic ramjet, which I won't go into. But another issue was pointed out by Bob Zubin and Dana Andrews, that you're essentially passing through an interstellar medium, which is like an effective drag, and that acts to slow the vehicle down. So, so this is moving into one of my very few forays into breakthrough propulsion, which is to find an alternative solution to the interstellar ramjet issue, and it's very speculative. So I worked. So,
can I just ask a quick question?
Yeah.
How big would that ramjet intake have to be to work?
Oh, it's like 10,000 kilometers.
Holy cow! Okay.
It's huge. Yeah. There's been some good work done since. People like Robert Freeland published a paper on it, and Michael Minovich actually did a really good study, presented at Starship Congress 2013. I've got his huge report. I can't find anyone to review it. It was submitted to Jabez when I was editor, but I couldn't find anyone to review it because it was like just horrendously big. But you know, there's been lots of cool work done on trying to get that down and what sort of materials you'd use.
So this is Greg Mahalik at Aerospace. The numbers I've seen on this concept is that you would need a magnetic field that has about 10 to the 17th cubic meters of volume to capture 1 gram of hydrogen from interstellar space. Does that sound like numbers you've heard?
Obviously it's the velocity dependent, right? Because
but 1 gram isn't going to buy you much, no matter how fast you're going. So, and 10 to the 17th cubic meters is the volume of all the Earth's oceans. So that would take a tremendous amount of power just to generate that, right?
Yeah, so the thing is about the interstellar ramjet is, in principle, it's relativistic, so it's up at the 99% the speed of light even. I mean, you're probably familiar with the Tau Zero novel by Paul Anderson, which essentially uses a Bussard ramjet, and I think the brake stops working, so it circumnavigates the universe. But if you can go relativistic, 99.99% speed of light, then what is the flux? I mean, you can probably run the numbers. I haven't done it, but it's probably a much higher flux. So I assume it's velocity dependent. I can't remember the specific numbers in terms of how much is going in, but we can look those up. So I came up with a very unusual idea, which was, so it's black hole physics. So I worked with a student at the International Space University. So at the time I was the executive director of the Institute for Interstellar Studies, also called the Institute for Interstellar Studies in the US, which I co-founded. And I had an idea to use black hole physics to kind of try and address the interstellar ramjet. And it's never been published before, other than this ISU study, which my student, Andrew Alexander did. He did an excellent job. We did write a paper, but we never submitted it to the journal. But I do have a paper on my computer, and the idea was to use black hole physics. So let's see how this works. So you're all familiar, I'm sure, probably way more than me, with the GR metrics, the Schwarzschild metric, and so forth, and Hawking evaporation. So the Hawking evaporation equation, which says that black holes will radiate inversely proportional to their mass, the size, and the power. You can calculate the power. These are classical equations. And of course, we don't really have a good idea for what the spectral emission is. We think it's mostly quarks, leptons, and other things. So you can see the distribution there. But the black hole will go through several phases in its collapse. So if you take two particles, you can collide them together. Hopefully, you'll get an idea for the direction I'm heading. It will go through two phases. First of all, is the birth, the collision of two particles, so two masses. And then there's the balding phase, where you have the gravity and electromagnetic emission. And it sort of settles down, which is mostly characterized then by the three-part properties of mass, charge, and spin. Then you have the spin down phase, which is you have lots of radiation emission, and the spin begins to slow, and now it's just a system that has mass. And then you have the Schwarzschild phase, where the mass even leaks out, and eventually it heads down towards the Planck mass. This is the evaporation of the black hole entirely over time. Well, so anyone predicted where this was going? Interested to know. So at the time, when we did the study, which was back in, let me just have a look. So I did a study with Alexander in 2003, but I came up with the idea years before that. So yeah, 2001 was some of these papers. That must have been when I came up with the idea, which was at the time when they were building Large Hadron Collider. You may remember there was this concern that if you collide two 7 protons together, and there happens to be more than 3 spatial dimensions, that this could lead to gravitational collapse of the two particles within the Schwarzschild horizon, because it changes the nature of the Planck length. and the gravitational constant. So this is just showing you the values of the Planck length, which I'm sure you all know, and the Planck time and so forth. And this is what happens with the equations you get when you start to look at high dimensional physics. So you end up with a gravitational constant, which is a inverse function of the dimensionality, and the Planck mass you can see is there also. The Schwarzschild radius of collapse. So what I want you to imagine is these two protons being accelerated around in the collider at CERN, and so there was concern that, you know, could they actually create a black hole? Now, obviously, to us physicists, we know that's not a concern. It's just exciting, right? Because you potentially get lots of emission properties and it tells you a lot about the structure of the universe. But from the general public's perspective, it's like, wow, you're going to create a black hole. I think there was even a court case. But you know, they haven't created a black hole, but who knows with the upgrades. And you can see here the temperature of the black hole evaporation and the time of the evaporation. So these are the key equations. And so the idea was that in the Interstellar Ramjet, to go back to it, instead of worrying about these having to collect these high energy protons, is you somehow allow some of them to go through into a target chamber. And if they're at high enough energy that they collide through Hawking evaporation, they emit lots of particles, and then you can use some of those particles that are emitted as thrust generation. Okay, so that was the basic idea. And you can see here just some of the calculations of looking at how the evaporation changes with different collision energies. This is with a D equals 10 model, so 10 dimensions. This is just showing what happens, again, black hole mass in tera-electron volt, evaporation time, emission temperature, and below we've got more calculations. This is the one below is classical, the one above it is with a D equals 10 model. And what you can see is enormous changes in the evaporation time, and this is because the Planck mass has changed. And so here's an example of D equals 10 model compared to classical. You can see the Schwarzschild radius difference, the Hawking temperature, the evaporation time, and the emitted power. So it all changes. And this could be possibly the emission spectrum, which is mostly, in terms of charged particles that you could use for thrust generation, sort of quarks and leptons. So that was the idea. So we did that study. Most of the calculations were done by Andrew for his master's thesis, and that was submitted to the university. We wrote a paper, but we never submitted the paper to a journal. I'd like to pick up the work, but we never published it. And going back to my own philosophy at the beginning of not overselling an idea, we never actually folded it through to doing some rigorous calculations on the performance, because we didn't feel we had a good enough handle on the energy spectrum of the emission in terms of what actually is coming out of that Hawking evaporation. It just seemed, is it really 72% quarks and gluons? But it'd be trivial to do those sorts of calculations. But my feeling was that it would be very inefficient compared to competing schemes. So this was an idea to really address the Interstellar Ramjet, and it's one of my few forays into breakthrough propulsion, which I didn't publish. And you can see this is what it might look like. That ring there is actually a CERN collider. Okay, so that's what it's meant to be, and you can see a target chamber. So the idea was that the particles are somehow collected in that in that ring. They're accelerated round, and they're allowed to collide. I think in reality, it's very difficult to get them even to collide naturally. But it's something that can be looked at further. And this is what it might look like. And you might have seen this graphic before. This is actually my graphic from my black hole engine, but I've seen many people using it for various different propulsion illustrations, and it's actually a black hole engine. But the specific example uses, as I say, a large hadron collider kind of ring. But actually, there's alternative ideas that instead of using a ring, you just allow the particles to collide and pass straight through your engine and out the back. So this is, I don't think this is a credible idea at the moment. I'm not trying to say it is, but given this is a propellantless propulsion scheme, it's kind of relevant to this workshop. As I said, I'd like to do more on it. I also looked at Warp Drive a little bit. In fact, my entry into Interstellar Studies was with Warp Drive back in 2007. Like many others, inspired by papers by Cuvier and others. I published a couple of papers looking at the idea of the subject, mainly to teach myself the field. I concluded that it didn't look plausible at this time. I use the word problematic, looks problematic. Never used the word impossible, but there seems to be a lot of things ruling warp drive out at this time. I did work on a documentary shortly after, where we tried to build the most plausible warp drive we could. And again, this has never been published. This is just some illustrations from the documentary. And essentially, one of the problems with warp drive, it seems to me, is once you've got that bubble around the warp drive, you can't, it's decoupled from the surrounding Minkowski space. So you can't actually accelerate or decelerate the vehicle. So what you've got here is a huge chasm mirroring, right? This is very, very speculative. This is science fiction, essentially. And it creates the bubble around it and accelerates it at the same time. And at the other end, you have to have a ring which decelerates it at the other end. So this was the idea. And I still think this doesn't work and it breaks so many laws of physics. But it was fun to do. One of my few investigations into warp drive. So since then, I've not done any warp drive. However, I did have a little play with something this summer during the COVID crisis, just for fun. You know, I'm interested in mathematical problems. This is something called Gabriel's horn, which some of you might have heard of. It's just also known as Torricelli's trumpet. It's a mathematical function of 1 over x. And essentially, it's got some very interesting properties. If you basically work out the surface area of this structure, you can show that it's infinite, okay? You can see from the calculations that's the case. That's called the surface of revolution. Well, similarly, if you calculate the solid of revolution, you can show that, you know, within the boundary conditions used in this problem, that it never exceeds pi. And so what you end up with for solid of revolution is that it's finite because it doesn't exceed pi. And so what you have here is essentially a finite volume, but an infinite surface area, which, you know, doesn't make sense from like Euclidean geometry perspective, but it was considered a sort of mathematical paradox. Well, it seems to me that one of the interesting things about warp drive is that the playing around with metrics has potential applications. So I mentioned the Alcubierre metric. And of course, one of the problems with the Alcubierre metric is it produced this enormous energy densities, you know, in order to actually create that bubble structure. And so there was a paper shortly after by Chris van der Broek. I'm sure many of you are aware of this paper, where he looked at creating a microscopic bubble within a bubble, okay? And so I won't go through the maths here, but essentially in this diagram, what you can see is 2 regions of flat space and 2 transition regions, which is your wall thickness. And so outside of that on the left is Minkowskian space. And you've got a bubble within a bubble. And what's really interesting about this Van der Broek metric is it essentially has the properties of a finite surface area, but potentially, because the internal volume is dependent on the function 1 plus alpha, and alpha is arbitrarily large, you can expand it, you can inflate it. That means that the internal volume is potentially infinite. So you've got a finite surface area, but an infinite internal volume, which seems to me to be the opposite of Gabriel's horn, right? So now we couldn't realize such a structure within Euclidean geometry. And so this is one of the beautiful things about looking at exotic physics in terms of, you know, because no one can prove that wormholes or warp drives exist in the natural world, or we can produce one artificially. But we may be able to, you know, at a quantum level. That seems plausible to me. And so what if you could realize something like what I call inverse Gabriel's horn or the Van der Broek metric on a quantum level, and then you could pass information through it. Or even, you know, more beautiful would be if you could create a bubble and cause it to transport from one location to another. I mean, essentially that's a warp drive. And that is why I think the future of wormhole physics and warp drive physics actually is, in terms of taking it forward into a more credible regime and to bring it just out of the intellectual Gedanken experiments. I think we need to be getting into the laboratory in the same way that Sonny White was doing with Yeagerworks laboratory with his interferometer experiments. I think we need to be getting into the laboratory and thinking about the quantum level, quantum foam, and whether it's possible to inflate some of these curled up dimensions. One of the best ideas I've heard for how we could do this actually was published by Richard Debussy with his PhD supervisor, whose name forgets me. That was at one of the Texas universities. Baylor University. I forget his name, I'm afraid.
Jerry Cleaver.
Gerald Cleaver, that's right. Thank you very much. Yes, and I've met Gerald many times. Apologies, Gerald, if you're on the call and I forgot your name. But they had the idea that actually, if you could increase the density of one of these dimensions, and it would naturally cause the other dimensions to inflate. And that was published in his PhD thesis and several papers. And that's one of the few ideas I've heard about how you can actually engineer, the properties of space in terms of its curvature geometry. So, that's kind of one of my few forays recently into FTL kind of territory. One of the things I wanted to point to as I head towards the close in this presentation is I recently created something called the Interstellar Studies Bibliography, which is on the Interstellar Research Centre's website, which is the organisation I now represent. And you will find there's currently 1,400 papers almost listed in time, and you can see the sort of peaks and troughs of the field. What I want to do as time goes on, if I can find somebody else to work with me to do it, is to start to break that list up into categories. And that may include, some of the breakthrough propulsion fields, but the literature is just so vast that it's not something I can do on my own. But I would encourage you to visit the website, because it includes not just papers, but books, science fiction novels, projects, articles. So that's something I'm working on, to try and really build a reliable compendium of information for space propulsion, to include propellantless propulsion. I guess closing, most of my work, as I say, is propellant-based propulsion, mostly fusion, and also I've been working a lot in lasers sort of systems, but fusion is really my thing. So I'm not really a breakthrough person, but I've studied quantum mechanics and GR, so it's fun to delve into those fields. There's people on this call far more qualified than me to talk about this sort of stuff. But I think it's very important that we do look into these sorts of breakthrough propulsion technologies, and I'd like to see us move more into an experimental regime. And I think this is important in terms of how we sell it from an investment perspective, because I've also been an investor in the past, invested in companies and initiatives and projects and programs, and it's something that drives you. I tend to be I'm a bad investor, if I'm honest with you. Most investors will invest based on the return. I take a long-term view and I never get anything back. But anyway, that's because I'm not good at it. But I've invested in lots of technologies and stuff, and hopefully one day one rooster will come in. But I think it's important to keep the field as credible as we can, and to not oversell the technology, but to really, if we can get into a lab and start to investigate some of this stuff, that's really what we need to be doing. So I think that's my last slide, and I'm going to leave this one up so you can stare at it while I take any questions.
Thanks very much, Kelvin. That was awesome. Thanks for your enthusiasm, and thanks also for rushing back from your ballet recital from your two little girls to do the talk. And I know you built this talk up sort of in the morning for the afternoon session for you. So greatly appreciated. Are there any questions for Kelvin?
This is Greg Mahalik at Aerospace. Yeah, that was a really good paper, and I really love this chart. The way you have it described here with the different types of what drives the designs here. Back in that Interstellar bibliography, did you have an algorithm or a set of keywords or something and different sources that you went to pull those types of papers from?
No, what I literally did was, so I used to be the chief editor of JBiz for 4.5 years. So when I was editor of JBiz, the first thing I did is created the red covers listing from all the famous red covers, and I sort of distributed them around the world to make sure people had a copy. So I expanded on that list. So I started with that list, so all the red covers of JBiz, and then I literally sat down and went through like the website of Icarus, Spacecraft and Rockets, Acta Astronautica, and other journals. So if anyone looks at that list and says, "Oh, my paper's not on that list," just send me your list and I'll add them. Okay. So
okay.
I want to find some students to work with me to help build that list up. But
right,
they're not categorized. What they are is in years. So 2020, sure. 2019, all the way back to early part of last century.
So are you going to be considering conference papers as well, or just journal published papers? Yeah.
So what my decision, and it's all on the website, is I only put papers on there which are published in journals, or they are proceedings of a conference or a
just hit the red button.
Okay.
Oh, okay. All right. Yeah. if they're conference proceedings, then that's good, because I know there's the STAFE conferences, the SPECIF conferences, the AIAA Propulsion and Energy conferences, the artist formerly known as the Joint Propulsion. Those had lots of different papers in the Nuclear and Future Flight Propulsion Technical Committees sessions, going back 20 years, right? And, probably another 400, 500 papers are in there.
Yeah, and you'll probably find there's hundreds of staff papers on there. I've personally added them.
Good.
And where I can, I actually get the papers myself as well. So I actually own an enormous collection of papers and also books. One of the projects I did in the summer is I got every single book on Interstellar. I sent it out to a whole bunch of people, about 12 people that I know who are in this field. Al Jackson and Greg Matloff in particular gave me lots of books I never knew about, so I immediately went and bought those. So I've got one of the biggest collections in Interstellar, and I'm making sure that the community is aware of them. Because what I find is there might be a lot of people in Europe that are not aware of some of the early American books. And there's a lot of Americans who aren't aware of some of the early European books, British books, like Arthur C. Clarke and Patrick Moore, who might talk about Interstellar, for example, or some of the scientists. There's books by Robert Broussard that are relevant to interstellar studies, but not necessarily about interstellar studies. So they're on there as well. And I've started also adding science fiction novels, which is, I think I'm asking for lots of work, but
Thank you.
Any other questions?
Yeah,
Okay, go ahead.
No, go ahead.
Oh, I just wanted to thank the speaker for just a really fascinating talk, and there's a lot to digest here, and a quick question: why does adding extra dimensions basically tone down the power spike on like this evaporating black hole business? Can you give us a quick explanation for that?
Well, for those that don't know, that's John Brandenburg. Just go ahead and introduce yourself before you start talking.
I'm terribly sorry. Yes, I'm John Brandenburg, and tomorrow I will be talking, and you will see the real gem theory stand up, which I first published in 1986. I got bragging rights for that name, which was from a box of paper clips, by the way, I found in my desk drawer.
Can you?
I'm sorry, Kevin. If you could just mention why having extra dimensions makes the black hole evaporation not be as big an explosion.
Well, okay, so I haven't done this for years, but I mean, if anyone knows immediately, feel free to answer, but I would suspect we can get the answer from the equation. So we go to the power equation. Let's have a look. So,
okay, so I see a dimensionality in the exponent.
Yep. I mean, it's what comes out of the maths, but in terms of physically why that happens, I can't recall. Anyone else want to answer that question?
No, but this is Jose Rodal. I would like to give you an example that addresses this issue, that you can have an infinite area surrounding a finite volume. And the example takes place in Euclidean space, the same space that we inhabit. Think of a coastline, like the coastline of Norway, that has fjords. And these fjords have infinitesimal depth, but you have an infinite number of them. Then the coastline is a line that has infinite length that surrounds a finite area. The same way, if you have a volume that is surrounded by an irregular surface, if the irregularity tends to infinity, but the height of the irregularity is infinitesimal, you can have an infinite area surrounding a finite volume.
Yes, does that basically speak to the black hole?
I was addressing first the example that he had with that Italian flute. Now, as far as the number of dimensions,
it's a trump, not a flute.
Sorry?
It's a trump, not a flute. It's a trumpet.
Okay, a musical instrument, but since we are short of time, can you please? Well, if you want, I can address the dimensionality in space-time, as you're showing there, the number of dimensions, and you know that in Riemannian geometry, there are certain things that can happen only with 3D space dimensions and one-time dimension. And as you increase the number of dimensions, then things can drastically change. And it is somewhat related, if you want, to this issue that I just showed you between fractal geometry embedded in Euclidean space. Because most pseudo-Riemannian geometries can be embedded, if you want, on a higher dimensional Euclidean space. So if you have to think of these geometries as not being Euclidean, but being irregular surfaces or irregular volumes that are embedded on a geometry that is familiar to you, which is Euclidean space. So you have to think of yourself as an ant, John Brandenburg being an insect that can only move on this irregular surface, and it cannot go out to the surface. And therefore, then you get an idea of what's happening.
Okay, thank you.
By the way, your inverse trumpet, the one with the infinite inside and the finite outside, that sort of struck me as being a reference to Doctor Who again and the TARDIS.
That's what I thought. So,
yeah, I thought, yeah, great minds, you know. Yeah. Anyway, we're actually doing quite well for time. Are there any other questions?
Hey,
No?
yeah, Kelvin, this is Max from Aerospace. Quick question about the black hole evaporator. Maybe I missed it. So you presumably have some fuel source or energy source to generate these black holes. Takes a lot of energy. Never mind the fact that you have a really powerful particle accelerator in a small space, right? So you generate the black holes, you somehow collimate the reaction products from the evaporation, get it out the back. All this takes a lot of energy. So why do this at all?
Yeah,
Why not just
I agree. So my motivation was trying to make the Interstellar Ramjet work, and at the time, as I say, there was stuff with CERN with the controversy over whether they could create a miniature black hole. So I thought that could be a solution. I agree. I think it would take a lot of energy. I mentioned I think it's very inefficient as a process. You know, I've not actually worked out how much bang you would get for your buck, as it were, but it's something I ought to do. And it was mainly because of the uncertainties over the emission spectrum. It was just guesswork in terms of working out. But you know, maybe I could do some parameter studies and make some assumptions. But I haven't worked in this for quite a few years, but it would be fun to pick up. But yes, it would take a lot of energy. And I mentioned that I think it's currently not plausible. But you know, there's a lot of clever people on this call even. So maybe some people could make it work.
cool? Thanks.
Hey, Kelvin, this is Greg Mahalik at Aerospace again. Can you just shout out your email address? Because I would like to correspond with you on a couple
Yeah,
of things.
sure. It's on the front of the slide. And maybe if I put the front slide up before Hal takes me off. Hang on. You should be able to see it on the slide. Or can you see it at the bottom? So it's interstellarresearchcenter@gmail.com.
Okay, and that goes directly to you?
Yep. It's just me.
But the center spelled R-E. Is the
Right,
English way.
right. I want to make sure I underline that.
Yeah.
So,
So,
thanks.
I won't go to the website. You better get me through there.
Kelvin, this is Jose Rodal again.
Thank you.
Which one is your favorite propulsion of all this propulsion landscape?
I think it depends on, I mean, that you're asking me to advocate based on subjectivity. I think it depends on the requirement, right? I mean, I am a fusion guy. I particularly, I do a lot of research into something called shock assisted fusion, which is an inertial confinement fusion system. I used to work with NIF quite a bit in my former job. So I am a fan of sort of successors to Daedalus, but it depends on the requirement. If I was to send the first without people, the first interstellar probe, I think Starshot is the right way to go. However, I prefer space-based beaming rather than ground-based beaming. And there's lots of reasons why they've gone to ground-based beaming, but I think space-based beaming is the best way to go. But we need to shrink that bob-forward architecture because, you know, Fresnel lenses of 500,000 tons is just unacceptable.
Thank you.
Thanks, Kelvin. That was great.